2.2, Graphs of Polynomials. We are going to start out with some vocabulary. So this first vocabulary term is polynomial. Polynomial is officially given a definition of this. However, I need you guys to understand that you know what polynomials are. It literally just means many terms. So anything with lots of terms all added together. For example, some of these are definitely things that you know. The next one is degree, and it's just the highest power or the highest exponent that appears in that polynomial. The term a sub n x to the n, I want you guys to notice that that's the first thing in the definition of the polynomial that shows up right here. So this is what we call the leading term. The next one, a sub n, you'll notice is just the coefficient of that leading term, and we call it a leading coefficient. And then a sub 0 shows up at the end here. All that means is it's the one with no variable, and we call it the constant term. Okay, those should all be familiar to you. Next, we're going to talk about the end behavior of various graphs. First one we're going to talk about is an even degree with a positive leading coefficient. So a good example of this would be like x squared, because 2 is an even degree and 1 is the coefficient, is a positive. So the easiest one to remember for this about what even positive graphs do is they do something similar to x squared. Both ends are headed upward. For an even negative, we do something similar, but we do it with negative x squared. Again, that 2 is even, but the negative 1 flips it upside down. So when you have an even degreed polynomial with a negative leading coefficient, both ends are going downward. For odd positive, we think x to the third, which looks like this. So we've got on the left side it going downward, on the right side it going upward, just like x to the third. And for odd negative, looks something like this. That one's a little squiggly, I apologize. But it should start at the top and head downward as it goes to the right. Next we have the following polynomial, and it wants us to identify kind of some of these traits that we just talked about. So the first thing I'm noticing is that the highest power is not coming first. It is not our leading coefficient right now. So I'm going to go ahead and fix that. I'm going to rewrite this as 11x to the fifth minus 4x squared plus 15x plus 32. Now that I've done that, it's far easier for me to see our leading coefficient is just 11. Our degree is just 5. They both come from that leading term. Then as far as end behavior goes, I know that my leading coefficient then is positive, and I know that my degree is odd. So just like x to the third, my end behavior is going to follow suit. So as x goes to infinity, what that means is as you go right, okay? As you go right, what is y doing? So as we move to the right, y is going upward. So we would say that f of x goes to infinity. Similarly, if we're talking about x going to negative infinity, that means we're moving left. So as we go left, our function is headed downward. So as x approaches negative infinity, f of x approaches also negative infinity. Okay. The next is in a slightly different form. It's in factored form instead. Oh, I apologize. I forgot to graph that sketch. So I don't really know what this middle part looks like, but I do know that this goes down, and I know that this goes up. We'll get to how we know what this does later. So next, for the next one, my leading coefficient is just the number. We usually actually call it a, okay? So there's your a. The degree, all you have to do is count up the exponents here. And don't forget that this one, since it doesn't have one, that's to the first power. So we're going to take that 2, that 1, and that 3 and add them together. That makes 1, 2, 3, 4, 5, 6 degrees. So since that has our 6 degrees, our end behavior is going to be a even negative. So even numbered degree, negative leading coefficient, which means it's going to be similar to an x squared. So as x approaches infinity, again, that means as we move to the right, and it's going to be going downward. And the nice thing about even degreed ones is they're both going to be the same no matter what. If you head left or right on x, they're going to go to the same place. They're both going to go down towards negative infinity. And again, I don't really know what the middle part of my graph looks like. I don't know, maybe it gets a little wonky. I really don't know, but they both head downward. Now for example 2, it's asking if the graph has an even or an odd degree. So what we are looking at to determine that is the ends here. So this end goes up and this end goes down. And as you notice up here, the only ones that go in opposite direction are indeed our odd polynomials. The even degreed polynomials either both go up or both go down. Okay, so we already know that this one has an odd degree. The next question is the leading coefficient positive or negative? So which side is going up or down now tells us this one. So because it's going up on the left and down on the right, that is what tells us that this one has a negative coefficient, just like negative x to the third would have. Now, the intermediate value theorem really just says that if you've got a point A and a point B, where A is less than B, meaning A is going to be to the left of B, then if one of them is negative and the other is positive, then somewhere you had to cross the x-axis, because the only way for f of A to be negative and f of B to be positive would be to at some point cross the negative side and get into the positive side. And in order to do that, you have to touch that 0. Okay, so all it's saying is that, hey, if this one's negative and this one's positive, somewhere in there we crossed. And then it could be true the other way also, right? Like if B was up here and A was down here, then somewhere right here you had to cross. Okay, the fundamental theorem of algebra states that for every degree of the polynomial, then there are that many complex roots. Okay, so if you have x to the 8th being the leading term, then there are 8 complex roots. If the equation is x to the 3rd minus 2x squared plus x minus 2, then it has 3 solutions. Okay, notice the word complex here. Some of them could be imaginary, and we will get into that. So then, if we have the polynomial function and x equals c, it has the multiplicity of m. Then if m is even, the graph turns and rebounds from the x-axis. If m is odd, the graph passes through and keeps going. So for example, like with x to the 3rd, that has a multiplicity of 3 at 0. So what it does is it kind of flattens out a little bit and then pops back up. Whereas like x squared has a multiplicity of 2 right there at 0, so it bounces off. Okay, or 1 is kind of an interesting one. So 1 is technically odd and it would just pass right on through, but it doesn't, but it goes straight through. Okay, whereas x to the 3rd does the kind of like flattens out a little bit first. The bigger the multiplicity is, the wider it gets right there. So for example, 4 looks a lot like 2, except for that the parabola is now wider. 5 looks a lot like 3, except for that flat part gets even wider. This question, is there a solution to this polynomial between x equals 0 and x equals 2? We use this intermediate value theorem. So we find f of 0. Okay, f of 0 is negative 2. And then we're going to go ahead and plug 2 in and find f of 2. So that comes out this way. You'll notice that 14 is positive. So somewhere between 0 and 2, we went from a negative y value to a positive y value. So the answer is yes. The reason is because, hey, we're negative over here, we're positive over here. Somewhere, in order to change from a negative y value to a positive y value, we had to have crossed the x-axis. So yes, there is a solution between 0 and 2. Do I know where that solution is? Not necessarily, but I know that it exists. Just to prove it to you, here is the graph And as you can see, there is indeed a 0 there between 0 and 2. In fact, it's at 1.58 something something, I don't know, but it is between 0 and 2. It's right there. For this graph, the graph of f of x equals -2 multiplied by x minus 2 squared multiplied by x plus 1, the first thing we're going to do here is find our x-intercepts so that we can sketch this graph. So our x-intercepts can be found by setting each factor equal to 0. So x minus 2 equals 0 and x plus 1 equals 0. Go ahead and solve there, and we get that x equals 2 and x equals -1. So that's where our zeros are. Or our x-intercepts, same thing, right? So then it wants us to find the multiplicity at those x-intercepts. So for this one, it's 2. Why is it 2? Because the degree of that factor is 2. This one is 1, because the degree of this factor, there's nothing there, which tells us it's 1. Okay? Then to find the y-intercept, we just need to plug 0 in for x, because the definition of a y-intercept is where x is 0. So we go ahead and plug that in. We can solve that now. So we get -2 out of the first factor, but we have to square it. We get 1 out of the second factor. I'm going to go ahead and ignore that one because it doesn't do anything. -2 squared is 4. Multiplying by -2 again, we get -8. Okay. So then it wants us to also determine the end behavior. Well, the degree is going to be all of your multiplicities totaled. Okay, so your total multiplicities, we have a point that has the multiplicity of 2 and a point that has the multiplicity of 1. Together that makes 3, which tells us that this is an odd degreed polynomial. Then we also need to check if our coefficient is positive or negative. Well, here's our leading coefficient. Is it positive or negative? It's negative. Now that tells us that our end behavior, because we are at an odd negative, should go up on the left side and down on the right side. So then the next job is to sketch a smooth curve that results from all of this. So I'm going to start by graphing our x-intercepts. There they are. Then I'm going to graph my y-intercept. Okay. And then I got to think about my multiplicities here. So 2 has a multiplicity of 2. So either it's going to go down and bounce off this way, or it's going to come up and bounce off this way. And in order to know, I need to think about my end behavior. So because my end behavior is going to go down over here, there's nothing between here and my end behavior to tell me to do something different. So that means that this is going to have to bounce off from the bottom. So that means it's going this way for sure, because it has to be able to connect into end behavior that goes down on that side. Okay. And then it's got to come down at least far enough to pass through our y-intercept. I think it's actually probably going to go that way. And I know that my left side also needs to be headed upward, okay, because of my odd negative characteristics. So then that means this one's going to be coming from up here to head down here. And then it's got to come down, and it has to hit that y-intercept, come back up, and bounce back off down. So give or take, that's what that one's going to look like. And in fact, let's go ahead and look at it in Desmos. There you have it. That looks pretty close to what ours. For example 5, we are going to start by looking at our leading term. So our leading term then has a positive coefficient, and it also has an odd degree. That tells us that our end behavior is going to look like this. It's going to be going down on the left, up on the right, because it's similar to x to the third. The next important point I'm going to talk about is our y-intercept. The definition of a y-intercept is where x equals 0. So we're going to go ahead and plug in 0 to find our y-intercept. That would look like this. Well, all three of those terms come out to be zeros. So our y-intercept then is at the point 0, 0. Next thing I have to do is find some x-intercepts. And just like y-intercepts are where x equals 0, x-intercepts are where y equals 0, or where the whole thing equals 0. Now in order to solve this, I'm going to factor out my x first. They all have an x. Okay, so I'm going to pull that one out. Then I have a really nice quadratic in here that I can factor. And in fact, it factors to x minus 8 multiplied by x plus 1. Okay. And then, of course, we still have our factor of x out in front, and it does still need to be equal to 0. I'll pause here. I just want to make sure you guys understand where I got that. Okay, so that's where our x minus 8 and our x plus 1 come from. Now we can just go ahead and solve for each of those factors. So the first one is easy, x equals 0. The second one, we do x minus 8 equals 0, so that comes out to be x equals positive 8. Then we do x plus 1 equals 0, which comes out to be x equals negative 1. All right, and you should have known that this one was coming because of where your y-intercept was anyway. So let's go ahead and use all of that information now to put it on a graph. So I'm going to put little notes to myself about where my end behavior is going to end up. I'm going to put a point on negative 1 for my x-intercept there. I'm going to put a point on 0 for my x-intercept there. And I'm going to put a point on 8 for my x-intercept there. Now, the y-intercept is already there because I did it with my x-intercepts. Okay. Now, I'm going to think about multiplicities. Well, the multiplicity of all of these factors is 1, which means it's just going to pass through all of these. So it's going to either go this way or this way. But because of my end behavior, I know that it's going to be headed from the bottom upward, because as you go left, it would head down. So this one I'm thinking looks something like that. And it's just going to pass on through. And at some point, it's got to turn around because it also needs to come through this one and just go straight on through. And then it's going to come down some. I don't know exactly how much. And then it's going to hit this one and continue all the way up. So I know this because I'm really just connecting dots, guys. So this one's headed down, but it's got to hit here. Okay, fine. And then it somehow has to go through here. I guess it has to turn around. And then it's somehow got to go through here. So I guess it turns around again. And then it's got to go up. Okay? Just so you've got your points at 0, negative 1, and 8. That's looking pretty good. This one does go down pretty dang far, so keep that in mind. But that does look like ours does. Next, it's asking us to create a polynomial just given some word descriptions. So it's telling us that the x-intercepts are at 9, 0, negative 8, 0, 5, 0, negative 2, 0, and that the leading term of p is 136x to the 4th. Mostly this is important because this to the 4th power tells me that the multiplicity of each of these is 1. Because if it's only to the 4th as its leading coefficient, it can't have more than 4 factors or more than 4 multiplicities. So we're just going to jump in then. That tells me that I have a factor of x minus 9 because of the 0 at 9, 0. And x plus 8, and x minus 5, and x plus 2. Those are just directly from those points up above. Now, I also know what the leading term is. So when I'm trying to do p of x, I need to add that leading term on. That's really it. Okay? We just take each of those pieces and put them where it's appropriate. Similarly, for this one, it's telling us it has a degree of 3. That's really the same thing as it was telling us here. It also has a root of multiplicity 2 at x equals 4 and a root of multiplicity 1 at x equals negative 3. It also tells us that the y-intercept is y equals negative 12, and it wants us to find a formula for it. So I'm going to write down a couple of things that we already know. So we know that we're trying to find g of x. We know that it has some leading term or leading coefficient. We don't know what it is. We know that it has a factor of x minus 4 squared because it has multiplicity 2. Remember, this has always got to be here with the opposite. We also know that it has a factor of x plus 3 with a multiplicity of 1. And we know that it has a y-intercept at negative 12. That's everything we know right now. What we don't know is that leading term. In order to find that leading term, we're going to plug 0 into this function and set it equal to negative 12 with leaving a with an unknown. We know that if you plug 0 into g, you're going to get negative 12 out. Okay, so we use that to our advantage. So that simplifies a little bit to negative 4 squared times by 3. And we know it has to equal negative 12 somehow. So then this gives us 16 times 3, still equaling negative 12 with our a multiplying in. So I'm going to flip that around and do 48a because I think that's just cleaner and easier to look at. And we know that it equals negative 12. So in order to get a now, I have to divide by that 48. And negative 12 over 48 reduces to negative 1/4. So now I know that my a, my leading coefficient, needs to be negative 1/4 in order for all of these other things to still be true. So all I have to do now is plug that in instead of a. And there you have your final g of x. It equals negative 1/4 multiplied by x minus 4 quantity squared multiplied by quantity of x plus 3. That's it. We also need to be able to take a graph and write the equation from that graph. So I will always start with looking at end behavior. These are both going up. Because they're both going up, that tells me that we're dealing with a function that has a positive even leading term. We also know from this graph that f of 0 equals 4 because that's where my y-intercept is on the graph. So in order to write this function, f of x, we don't know our leading term right now. But we do know it has a factor, or a 0, at negative 2, which means that we have a factor of x plus 2. We also know that we have a 0 at negative 1, which gives us a factor of x plus 1. Same with 1, therefore the factor is at negative 1, and 2, and therefore the factor is at x minus 2. Now, all of these are going straight through. None of them are bouncing or flattening out or anything. They are all going straight through, which tells me the multiplicity of each of these is 1, which is why I didn't write anything with them. So then we know that f of 0 has to equal 4, but we don't know our a. So we're going to go ahead and plug that 0 in and set it equal to 4 in order to find our a, or our leading term. So simplifying those down a little bit, we've got a times 2 times 1 times negative 1 times negative 2, which comes out to 4. So 4a has to equal 4. Well, then a is just 1, which means I don't actually need it, and I can just take my factors and go ahead and put them into that format. Okay. So let's try another one of those. Actually, let me go ahead and show you the Desmos graph just to show you that if you plug this equation into Desmos, you do get the same thing. We always want to double check our work. So here it is. You can see what I have typed in, and you can see we've got our zeros at negative 2, negative 1, 1, and 2, and a y-intercept at 4, and behavior is both going up. This is definitely the same graph that we were looking at, so we definitely did this correctly. So let's do another one. First, we look at our end behavior. That one's going up. That one's going down. That tells me that this is an odd degree with a negative. Okay. That tells me that I've got a 0 at negative 3. That tells me I've got a 0 at 1. And that tells me I have a y-intercept at 1. So there's your point 0, 1. This one I know has a multiplicity of 2. The reason I know it has a multiplicity of 2 is because it's hitting there and bouncing right back off. This one has a multiplicity of 3. I know because it kind of flattens out a little bit and then goes through. So with multiplicity of 2, this one should have the factor of x plus 3 squared. And with a multiplicity of 3, this one should have a factor of x minus 1 to the third. So then we have to write it. I don't know my a. I don't know my leading term right now, so I'm going to leave it as just some a. But I do know that we've got an x plus 3 squared, and I know I've got an x minus 1 to the third. I also know that g of 0 is supposed to equal 1. So if we plug 0 in and set it equal to 1, we should be able to find our a. So that simplifies down to 3 squared and negative 1 cubed equaling 1. And then that becomes 3 squared is 9. Negative 1 cubed is negative 1. 9 times negative 1 is, of course, just negative 9. And so 1 divided by negative 9 is negative 1/9. So there's our a value. And then we can just go ahead and plug it into that function we already knew. So we put negative 1/9 in for a. We still have our x plus 3 squared and our x minus 1 to the third. There we go.